So we're going to define the derivative of the tan function, and the defined derivative of tan function is secant squared. So again, we're not going to prove this. We're going to try to justify it the best we can, but we're not going to prove this by any means. Okay, so this derivative of this function is secant squared. So if I differentiate this tan function, I can just look at some of the slope values here. So as it goes to the x-axis, that slope happens to be a slope of 1. Okay, so it gives us a y-coordinate here. And notice that it gets more and more steep, okay, through there. So what's happening to a tan function? Yeah, it's a secant squared function. Secant squared function looks like this. It's getting more and more steep, and it's going to vertical asymptote at pi over 2, because again, the vertical asymptote here at pi over 2, the slope is undefined, okay, it's going infinite, so the slope is going infinite as well. And so it does the opposite here. It starts off as an infinite slope at this asymptote, and it kind of goes down to positive 1, goes through the, so it's doing the same thing symmetrically on this side. Okay, so this is, we're going to define the derivative of tan is the secant squared function. Again, this is by no means a proof of it, but we're kind of trying to justify this result. So this is more of a definition than anything. Okay, so these are things that you can put on a formula sheet. You need to know these ones. You need to remember these ones. For now, these, definitely use a formula sheet until we get used to them, but we will get used to them, and these are going to end up being just defined derivatives. So same with secant. The derivative of secant is secant x tan x. So here's a secant function, okay, and we can see that the graph of the secant function, the secant x tan x function, seems to be at least not conflict with the slopes of the secant graph. So if we notice here, the slope is near 0, it's near horizontal. You notice that the y values are near horizontal here, and as we, in fact, it is horizontal at that point right through there, because that's a vertex, and it hits the 0 there. It becomes more and more negative to infinity. Yeah, it's going more and more negative. That's a negative slope here, okay, and negative infinite slope. Yeah, it's going from negative infinity. It goes to 0. Yeah, it goes to 0. And then now the slope's going from negative to positive symmetrically. Yeah, it's going negative to positive. Positive infinite slope at the asymptote. Yeah, going through there, that's a positive infinite slope. If you can't see it, it's kind of slanting that way, right? So it's positive infinite slope, and it goes down to 0. So notice that this graph is going down to 0. Okay, and again, I'll just mark out the horizontal tangents here, here, and here. Yeah, we have zeros here, here, and here for the secant x tan graph. So same thing here. The derivative of cosecant is negative cosecant x. And again, we don't justify this. We're not going to justify this at all, other than, we're not going to prove this at all, other than this now is something we've put on our formula sheet. Okay, so same thing with cotan. The cotan function is going to be defined as secant cosecant squared, negative cosecant squared x. And again, we don't really justify, we're not going to prove this, but we're going to look at the graphs and we're going to see if we can justify this result.